Welcome to my YouTube channel. In this video, we are going to look how to calculate seismic load based upon Russian standard. In the right hand side, you can see a PDF file SNIP 2781 which is recorded for seismic load calculation based upon Russian standard. In the left hand side, you can see an Excel sheet which is developed to demonstrate seismic load calculation based upon Russian standard. First input we record is a seismic magnitude which is having the range of 7 to 9. This is as per technical specification or project requirement. Second one is a soil profile. This is to be referred from soil investigation report or any geotechnical requirement from the project team. Generally this soil profile is classified from 1 to 3. This is as per table 1 of SNIP 2781. 1 is mean for a rock of all types. 2 is weathered and heavily weathered rock. 3 is loose sands, gravelly, coarse and medium grain. For the classification of soil profile based upon the SNIP standard, we need to refer page number 6 in the right hand side of PDF. So here you can see in the table 1, the classification are well explained. Then the next input is a numerical factor for seismic magnitude 8 which we had chosen or we had given as an input. So for that we need to refer class number 2.5 2 notes of SNIP 2781. The page number 9 to be referred in the right hand side PDF. So here you can see A equal to numerical factor 0.1, 0.2 or 0.4 for seismic magnitude 7, 8 or 9 respectively. So in our case, our seismic magnitude is 8. So the value is 0.2 which is picked from the input which we had given as a seismic magnitude 8. And the total height of structure we are assuming as a 10 meter. And the next one is we need to find out the fundamental period of vibration T1. For that there are two methods I am showing here. One is we need to develop a model in StatPro or any of the software, structural software, and we need to run an analysis using other code like UBC or European standard or Indian standard or whatever the requirement we are having in us, and we need to find out the aging solution or the frequency applied on the structure. So I had done a stat model for that, and I had find out the frequency is 3.6 cycle per second. Then the fundamental period of vibration is nothing but it is a reverse of frequency. So it is 1 divided by frequency. So 1 divided by 3.6 is 0.28 second I am getting. Alternately, we can find out this fundamental period using the formula from various other standards like European I had shown here. EN 1998 part 1 to be referred for this. So here the formula is given as CT into H power 3 by 4. CT value is varies depends upon the moment resistant structures and non-moment resistant structure. For non-moment resistant structures it is 0.05 and for moment resistant structure it is 0.085. So likewise I had calculated the same value of 0.28 second and is coming. So I am considering 0.28 second. Next one is a dynamic coefficient. This is we need to refer as per class 26 of SNIP 2781. For that we need to refer page number 9. It is here. Dynamic response factor is responding to height period of the building or structure shall be determined in accordance with the section 2.6. So here is the formula. If T1 is less than 0.1 second, this is a formula Pi equal to 1 plus 15 Ti to find out the beta value. that is a dynamic coefficient. And in case if Ti is greater than 0.1 second and less than 0.4 second, we need to consider 2.5 as a beta value. And the third one is T1. If it is greater than or equal to 0.4 second, then the beta value is Bi equal to 2.5, 0.4 divided by Ti power 0.5. So our case is our fundamental period of vibration is 0.2 second, which is lying in the second option. So our beta value is 2.5. So here 2.5 is calculated as a dynamic coefficient. Then the next one is a structure character. For this definition of a structure character, we need to refer table 6 of SNIP 2781. For that, we need to refer page number 12. So in page 12, you can see here the table 6. So tall structures with relative support footprints, it is 1.5, that including tower, mast, smokestacks, detached elevator shafts, etc. Building with the supports at first story and drift ratio of the first story to the story above. So these are the things we need to consider. K value, which is a structural characteristic factors, as 1.5. And building frames systems in which all fillings do not affect buildings deformability means it is 1.3. Buildings and structures non-listed in items 1 and 2, it is 1. So for our category, we are considering tall structures building, high-rise structures of a small size in plan, tower, mast, chimneys. So this is a tower mast which we are considering, so it is 1.5. Then the next one is the seismic load value. So for that we need to refer class 2.5 2 of SNIP 2781. We need to refer page number 9 for this. So here you can see the formula to calculate the seismic load value. SOIK equal to QK into A beta I KW NIK. So we had almost calculated all the factors. So the QK is nothing but it is a mass, and A is 0.2, beta 2.5, and K phi is 1.5. So QK is a mass of the structure. Here you can see here in the right hand side PDF file, QK equal to weight of the building or structure related to point K. So that we had assumed here as 10 kilonewton. You can see here QK equal to 10 kilonewton. So I am missing here while calculating this SOIK, the Q value alone. Later we need to multiply this QK, that is the weight of the building, into the SOIK calculation. Then the next one is we need to find out as per this formula SIK equal to K1 of SOIK. So in this, it is a design seismic load SIK. So for that we need to find out the K1 value. We need to refer table 3 of SNIP 2781. For that page number 12 to be referred. So here you can see in the right hand side the table 3 of SNIP 2781. So here I am having three various structures which are listed based upon the table 3. So if I am selecting the structure in which no damages and need, that is the first case, the value to be value of K1, that is the structural behavioral factor, is 1. So similarly, like if I am selecting the building with the large panel reinforcement concrete structure, it is 0.2. For our case, it is a steel frame without steel frames with a diaphragm. So if I am selecting the steel frames without vertical diaphragms or ties, means K1 factor is 0.25 as per the table 3. So likewise we need to select from this. So it is for temporary structures. So for our case, it is steel frames with diaphragm or ties, I am assuming. So for that K1 factor is 0.2. So all these table values of SNAP 2781 are recorded here in the right hand side of a sheet, in Excel sheet, left hand side Excel sheet. So you can see here. So these are the table value which are captured here from the Russian standard for Smith, and these values are captured based upon the input which we are providing here. So next one is total weight, which we already assumed this as a 10 kilonewton. Next one is a design seismic coefficient, which is given in the class 2.51 of SNAP, that is page number 9. So here you can see in the right hand side PDF file, SIK equal to K1 SOIK. So by applying this formula, now we had find out SIK value, that is design seismic coefficient. I'm just multiplying that K1 into SOIK, 0.22 into 0.75, I'm getting 0.17 as my design seismic coefficient. Finally, the base shear force due to seismic we are calculating, that is SIK into QK. QK here we had missed out while calculating the SOIK. I am multiplying that QK, that is weight of building or the structures, into this SIK value. Now I am getting the seismic base shear force as 1.7. So now this force to be applied based upon the structural model in each individual panel to find out the final seismic base shear force at the base. So with this I will stop this session. We will see in another session. Thank you. Look description for more related videos.